Okay, so now we're going to talk about isoclines. And an isocline of a differential equation is of the form y prime of f of t given a differential equation of this kind. We're talking about first orders here. It does not have to be linear. Where f of t is what's on this side, is a curve of the form f t y equals some c, where c is a constant. So these are just lines. Isoclines are lines when we set the derivative to be a constant. So let's look at an example of some isoclines. And c can be any constant for any kind of isocline. When 0, we call them null clines for nothing. Okay, so here's my differential equation. And so my f of t is this whole function. And so to find an isocline, we just set it equal to be a constant. So c is a constant. And then let me just solve this. So these are all my isoclines. They can be anything. You can make c equal 1. This is an isocline. You could make c equal -2. You could make c equal pi. They're just some constant. But what do these isoclines look like? These isoclines all look like parabolas, right? So like if I was going to graph these, we'd have t squared plus 1, t squared minus 2, 1, 2. And that shouldn't have been so fat. And then pi is, there's 1, 2, 3, there's pi somewhere around here. But they all look like parabolas, right? So parabolas. So why isoclines are useful, we're gonna, all of these values, wherever these parabolas are, they have the same derivative. So on a given isocline, the derivative is the same. Derivative is the same. So if this was my directional field, this one was pi, so I know that my slope is 3.14. So everywhere on here, my slope direction field is here. Let me draw the arrows with a different thing. And this one is -2. I know all of these slopes on this, so these are just points on this parabola, and they're all -2. And this one is all +1. So that's why this is helpful to solving these. So let's look, we're going to look at next an example of using isoclines to solve a direction field. Okay.